the Evans rules. There is a set of rules that assist in drawing the root locus. They are in the number of 6. So the first Evans rule states that there are n loci, as many as the system order. The system order is the degree of the polynomial, of the S polynomial at the denominator. So in this example, in which we have an order 3 system, look, the denominator is a polynomial of the 3rd degree in S. We will have 3 loci, 3 trajectories, which represent the loci of the closed loop poles when k is raised from 0 up to plus infinity. The second Evans rule states that the loci start from the open loop poles and terminate at the zeros of the open loop system, including infinity as special zeros. The third Evans rule is considering the real axis and is able of discriminating which parts of the real axis are actually part of the root loci. And the third Evans rule states that real axis sections of the root loci exist only where there is an odd number of poles and zeros to the right of our current point. The roots with imaginary parts do not interfere in this, because they always appear with their conjugate partner, and they do not influence this. The fourth rule concerns the existence of asymptotes, which are the straight line directions to which trajectories that are not terminating in zeros have to follow to go to infinity, which is also our case. The number of asymptotes is equal to the difference to the number of poles and the number of zeros. So in our example, we will have 2 asymptotes, because we have 3 poles in our example and 1 zero. The asymptotes are equally spaced as far as their angle. They form angles with the real axis that are calculated by this formula. 2k plus 1p Greek divided by q, where q is the number of asymptotes, and k is an integer parameter increasing from 0 up to q minus 1. The next point is, where are those asymptotes located? Or better, where is the intersection center? They define a family of straight lines all centered in one point, which is the gravity center of the asymptotes, and can be calculated by this formula. They move to infinity, one to plus infinity, and the other one to minus infinity, by approaching the asymptotes, as long as k is increased from 0 up to plus infinity. Evans rule number 5 refers strictly to the case when at least one branch of our root locus is on the real axis. And there is a special point on the real axis from which 2 or more trajectories intersect and after that leave the real axis, like here, or vice versa, 2 or more trajectories intersect when coming from the upper and the lower half plane, and after such an intersection conflict, they move on the real axis. Look here, the leftmost upper example. We have 2 poles on the real axis, as represented by crosses. the right part of the real axis is not a section of the root locus. The leftmost part of the real axis is not a section of the root locus because of the consequences of the rule number 3, the Evans rule number 3, concerning the evaluation whether a point on the real axis is part or is not of the root locus. So only this segment included between the two poles is part of the root locus. But according to the rule number 2, you know that from each pole a trajectory has to start. So we will have a trajectory starting from the rightmost pole and moving to the left, and another trajectory starting from the leftmost pole and moving to the right. Those trajectories are obliged to remain on the real axis because that section, this segment on the real axis, is part of the root locus according to rule number 3. So when increasing k, the closed loop poles move toward each other and up to a point in which they hit each other. The intersection or the conflict point is referred to as breakaway point. After that, the trajectories have to go on. They must proceed further. The only way they can proceed is that of leaving the real axis and going in a symmetrical way in the one in the upper and the second one in the lower half plane. In the first two examples, the breakaway point is a real point, although it is a negative one in these examples. It is possible to calculate the coordinate of the breakaway point by means of this equation. The sum of the fractions which are given as the reciprocal of the Laplace abscissa minus each and all of the zeros. So this is 1 divided s minus z sub I. So we have to sum all the fractions that we obtain while putting at the denominator a binomial in which we have the difference between s and the generic 0. And we have to carry out the sum over all the m zeros we have in our original transfer function. And similarly, at the right-hand side, we have a fraction which is obtained by taking the reciprocal of s minus p sub j. So by taking the sum of all the fractions that have at the denominator the difference between the Laplace abscissa and each pole from our original transfer functions. This is an algebraic equation in the unknown s. In most cases, s would be a real number for a breakaway point. So what's the degree for the resulting algebraic equation? The degree is n, because you will have a common denominator here, which is the product of n binomials, each one containing s. An algebraic equation of degree n will have n roots. Are you expecting n breakaway points? No, because most of the solutions of this equation would give values for the complex variable s, which are not compatible with the root locus. So this equation is providing us the coordinates of the breakaway points. Evans demonstrated that this equation can be obtained by setting that k as a parameter depending on s, because k is actually changing when we plot the locus. And as a consequence, the closed loop transfer function poles are setting different values for s as long as k is changed. So the idea was that of evaluating the derivative of k with respect to s and setting such a derivative equal to 0, which implies looking for a maximum or a minimum in a hypothetical function which establishes how k is changing with s. So after some manipulation related to the use of derivative, gh of s is the open loop transfer function of our process, we at the end obtain this equation, because d of s is in this symbols is the denominator of the transfer function, which is expressed as a polynomial. Look, the transfer function is a rational function. gh of s is the ratio of two polynomials in s. The numerator is a polynomial of degree m, and the denominator is a polynomial of degree n. And you know, here there is also the dual case. This is a perfectly dual case. Here we have two zeros on the real axis and two trajectories coming from poles that are located elsewhere on the complex plane. The two trajectories move according to the Evans rule number q. The two trajectories which started from open loop poles have to terminate on top open loop zeros. So they have to terminate on top the two circles that we see here, representing open loop zeros. So they come from the upper and the lower half plane, and they have to land on the real axis, and then each one of them has to go toward each one of the two open loop zeros. So they once they land on the real axis, they hit each other. There is an intersection point. So there is a breakaway, and at the breakaway point, they are going toward opposite direction. One to the right and the other one to the left. So this is again a breakaway point, but there is a difference. This is a breakaway point for trajectories entering the real axis, whereas the first one is a breakaway point for trajectories leaving the real axis. Well, the second point is that addressed here. How much is the angle? So what's the typical pattern, or more in a more quantitative way, how much is angle that a trajectory is assuming when leaving or when entering the real axis? Well, the angle is can be calculated as a submultiple of the plane angle. Angle of breakaway is P Greek, or if you like, 180 degrees, divided by K, where K is the number of converging or emerging loci. So, when we go back here, how many loci do we have emerging from the breakaway point? And here, how many loci do we have converging into the breakaway point? They are 2. So the angle that each trajectory is forming with respect to the positive direction of the real axis when leaving or when entering the breakaway point is the P Greek divided by Q, which becomes 90 degrees. And this appears reported in this example graphs as a small square. Small square indicates that we have a right angle at the breakaway point. Clear? But it is possible that the trajectories are more than Q. So look at this very complex case. This is a very, it's like of star. It's a very, very special case. We have 4 poles and no zeros. All the trajectories leaving from poles converge into the same point. In this case, they are 4. From left, 1. From right, 2. From below, 3. And from the top, 4. So the breakaway point is involving 4 trajectories. So 4 trajectories are entering and 4 trajectories are leaving. Only 2 of them are part of the real axis, the left one and the right one. The calculation formula for the breakaway coordinate is always the same. The angle, the simple formula to calculate the angles is again the same, but in this case k equals 4. And so the angle that the first trajectory forms with respect to the direction, the positive direction of the real axis would be P Greek divided by 4, so that is 45 degrees. Anyway, it is easy to make the other calculations, or in a simpler way to understand the graph, because please remember that the root locus is always symmetrical. So if there is a trajectory emerging with an angle of plus 45, for sure we will have another trajectory emerging with an angle of minus 45, which is this one. And the other trajectories would be the complementary, so the trajectories lying on the same straight line, but moving toward the opposite direction. So this is an angle of 135, and this is an angle of minus 135 degrees. Questions? Before going on, there is even a more complex case here, more complicated case. I should not confuse complex with complicate. A more complicated case in which we do have two more breakaway points, one here and another one here, which this time are complex points with both a real and an imaginary part. So this corresponds to roots of this equation that are not real but complex. And you know that for an algebraic equation having real coefficients, when you get a complex root, you may be sure that you will have also its conjugate pair as a root of the same equation. So if we solve that equation and we find this point to be a breakaway point, we may be sure that also the conjugate point, that is this one, would be and is a root of this equation. You may ask me, but what's the difference between the two cases in the lower row? Perhaps it is better that we will discuss examples like this when using MATLAB, and so in the lab class rather than here. Because in principle, look, the pole position, the open loop pole position is the same in the left case and in the right case. We have, in some way, we have a cross of poles. Two of them being on real axis, on the negative real axis, and other two of them being complex and conjugate. So why should the root locus be different when we have the same, let me say, geographical mapping of poles? The reason is that this depends on the transfer function, on the open loop transfer function. So on the numbers, on the coefficients that are inside it. So because you may understand this, because even though the degree of the equation changes, you may have different equations when changing the numerical values for zeros and poles. In practice, you know, if you fix the degree of a polynomial equation, no? In this equation, in this case, the degree would be 4 because 4 poles are shown. No? You know, there are infinite algebraic equations of degree 4, depending on the infinite number of choice that you have for the equation coefficients. So when changing the coefficients, the mapping of the loci changes. And you may switch from a situation like this to another one like that, or even to to other possible situations. So another possibility would be that the two trajectories leaving from here would not merge here, but would go directly to infinite. So it depends on the numbers. It depends on the values of the coefficients you have, which in turns depends on the numerical values of zeros and poles in your original open loop transfer function. Here there is a solved example for a transfer function in a factorized form. And it is also in the pole and zero form. And we have 3 poles. One is at the origin, as you may immediately understand from here, from the factor s. And 2 are at -3, because there is a multiple root, as you may understand from the squared factor here at the denominator. So the fact that we have a double root or a double pole at -3 is noticed here by double crossing that point. So there are 2 overlapped, almost overlapped crosses. So we may land on top the final Evans rule, which is the rule number 6. The rule number 6 deals with the angle that is necessary to calculate to determine the direction by which each branch, each part, so each locus on the root locus, on the complex plane, the angle that each branch or each locus is following when leaving from a pole or when terminating on a 0. So the 6th rule allows determination of the angle of departure from a pole and the angle of arrival to a 0. Let us consider the simplest case. In the simplest case, we have poles, open loop poles, and open loop zeros lying on the real axis. In that case, it is not necessary to use any formula. The answer is immediate. The departure angle or the arrival angle would be 0 or pi Greek always. Let's look at examples. Here we have 2 poles. Now we are focusing on departure angles because we have poles only in this example. Well, for sure one trajectory is leaving from the rightmost pole and going to the left. And for sure another trajectory is leaving from the leftmost pole and going to the right. So the angle that the rightmost trajectory has to follow at departure must be pi Greek necessarily. Similarly, the angle that the trajectory leaving from the leftmost pole has to show with respect to the positive direction of the real axis must necessarily be 0, because such a trajectory is obliged to move on the real axis. Similarly, for zeros lying on the real axis, the arrival angle, here we are interested in the arrival angle. So the last angle, just the ultimate angle that the trajectory is forming when k is approaching infinity. By inspection, again, the angle can be 0 or pi Greek only. In this case, the angle would be 0 because the trajectory is equally oriented with respect to the positive real axis. In the left case, the angle, the arrival angle, would be pi Greek. The situation is more complicated when departure poles or arrival zeros are complex. Like in this case, in this example, we have 3 poles, 2 of them being complex and conjugate, and we have 1 0. So this section on the real axis is a part of the root locus according to the Evans rule number 3. The formulas that give the angle, look, the angle is displayed here graphically. are derived from the angle criterion and are reported here. The first formula is calculating the angle that a trajectory leaving from a generic pole P sub A is forming with respect to the positive real axis. Such an angle is considering the possibility that the generic pole P sub A is a multiple pole. So there are many crosses overlapped on the same point, and the number of poles, so the multiplicity is Q. So the formula is parametric in K, because if this is a multiple pole, according to the Evans rule number Q, Q trajectories have to leave from this pole. A multiple pole is giving rise to multiple trajectories, as many as the pole multiplicity. And so the angle would be different. And then the formula is taking the sum of all angles formed by the complex number obtained by subtracting each zero to the current pole. Here we have P sub A minus Z sub I. And I is the zero index changing from 1 to M. And then we subtract all angles formed by the complex number obtained by subtracting each pole to the current pole, where J is the counter for poles, and is going from 1 to N. And here we have to neglect the case where the pole Pj is equal to the current pole. The P sub A is one of the poles. So when we run the counter J, at a certain point we find the same pole that we are using. So there is one pole for which J equals A. Similarly, it is possible to calculate the angles for trajectories approaching a zero of multiplicity Ni, larger than 1. And the formula is in principle the same. So an odd number of times P Greek, similarly, plus the sum of angles that is formed by the complex number obtained by subtracting each pole to the current zero, ZB minus PJ, minus the sum of angle formed by each complex number obtained by subtracting each zero to the current zero with the exclusion of the current one, I different from B.